right, so today's lesson is basically about the main vocab going around this idea of periodic motion. So, to start off, periodic motion refers to any sort of repeated motion, a motion that repeats itself in evenly spaced increments of time along the same path. Like if I run laps at the track, or if I swim laps in a pool. Periodic motion would be some sort of motion that repeats itself. Can you name me other things that are examples of periodic motion? All right, so we got a pendulum. What else do we have? Kids at home, you can just unmute yourself whenever.
The drinky bird.
Oh yeah, the drinky bird. I forgot about him. I should go fill him back up. He's sitting in the back of the room. The drinky bird is a periodic motion. It repeats itself every minute or so, evenly spaced increments of time, and just one path. Do you have any periodic motions that occur in a human body? Heart is one. How about one more? You're right, your heart beats something like 60 to 80 times per minute when you're resting, maybe a little bit lower. Right. Blinking is about once every 3 or 4 seconds, but when you think about it, then it changes. As soon as you start thinking about it, you're like, wait, has it been 3 seconds? How often do I blink? Am I just holding my eyes open now? How about, oh yeah, I guess you could say breathing. Yeah, breathing's a good one. Right? So I don't know the breaths per second or the breaths per minute for a person, but I feel like that's got to be probably pretty regular. Ooh, how about ones in space? Can you name me ones in space?
The Earth revolving the sun.
Yep, Earth revolving around the sun, the moon revolving around the Earth. So here are my examples of periodic motion. I think we got them all. We had a pendulum. We had the Earth revolving around the sun. We got a heartbeat. We got eyes blinking. Ooh, and I added a new one. Waves. All waves start with oscillations. They start with periodic motion that goes up and down. And as a wave travels, that one bit of water that makes up the wave goes up and down in place. We'll talk more about wave mechanics later this week, probably Friday. Okay, so periodic motion is this big class of categories, things that repeat themselves. A subsection would be called an oscillation or vibration. You and I are going to call those the same thing. We're going to call those synonyms of each other. So an oscillation or vibration is going to be the same thing. So it's a periodic motion. So it's a motion that repeats itself in even increments of time along the same path. So it's going to do all the same things a regular periodic motion does. But now it's going to do this around a specific point called your equilibrium position. I bet, can someone draw? Someone at home that's doing like the annotate the screen for me? Annotate the screen and mark the equilibrium position for me. To the point that all of these spheres are oscillating around, right in the center. That is your equilibrium position, the point around which everything else is oscillating. Okay, so we've got an oscillation. It's this regular variation in position around a certain point, and we call it certain point in the middle. That is your equilibrium position. So it's a special type of periodic motion. You've got that vibration along a specific point. In this case, you had your equilibrium position as the rest position of your symbol, and it oscillates up and down around that equilibrium position. Those actually create sound waves. They push the air around them. And you can kind of see it with the sand they put on the symbol. It pushes the air around them so that the air now vibrates with the same frequency. Right? Mathematically, a vibrating cymbal looks something like this. It makes waves. In this case, they're oscillations that go around that specific point. But the waves of sound would then spread out from this source. So, how do we talk about vibrations or oscillations? There's 2 ways we can talk about them. We can talk about how big they are, and we would call that an amplitude. And we can talk about how much time they take, and that'll be something else. Okay, so new vocab word. This is amplitude. Its symbol is A, and it has various units. If you're thinking to yourself, like, why would it be various units? Because it depends on the system we look at. So let me point out where amplitude is on this picture. If you take your equilibrium position, and in this case, the equilibrium position is this nice calm sea level right here. Amplitude is the distance above it. So the distance from equilibrium to crest, or equilibrium to trough. That would be amplitude. And since in this case of a literal water wave, in this case, because that's an actual distance, its unit for amplitude would be meters. And that's probably the easiest one to picture, right? You're like, okay, it goes up and down. So we measure up and down distances with a meter stick. We would measure that in meters. Okay. So notice in order to get the amplitude, I found the equilibrium position, and then I'm labeling the distance from equilibrium to crest or equilibrium to trough. Okay, but the reason I said it's various units is what if I did instead a pendulum, right? So I'm going to do the same thing. I'm going to mark the equilibrium position. The equilibrium position for this pendulum is here. Let's make that a straight line. But notice that it's amplitude. You could measure it at a distance, but we could actually measure this amplitude with angles. We could measure the amplitude in this case in degrees. So amplitude for a pendulum would be measured in degrees. Amplitude has units that make sense for the system you're working with. If it's a wave, maybe like an earthquake wave. If it's an earthquake wave, I could literally go out and measure that with a meter stick. Or I could measure in centimeters the deflection of the little seismograph from rest. In this case, I would measure it in degrees for a pendulum. If it were something like sound is a pressure wave. Since sound is a pressure wave, its amplitude would either be measured in pascals, which is your base unit for sound pressure. It's actually your base unit for any pressure. Or decibels, which has to do with loudness. We're not really going to talk about pascals too much. We will talk about decibels when we get to loudness, because the loudness of the sound does depend on the amplitude of the wave. Think like more amplitude, the louder it is. But it has to be in the range of human hearing, and that's where the decibels comes in. Decibels takes into account how much pressure is there, and can you actually hear that noise? If I had a dog whistle and blew it, it would have a really high amplitude, but zero loudness, because our ears are not sensitive to that frequency. So lots of the time, amplitude is just going to have a unit that makes sense for the system. One that we definitely will not do, but I want you to see. A light wave, light is an electromagnetic wave. It has an electric field that's red, that vibrates up and down. Electric field is measured in newtons per coulomb. And it also has a magnetic field that's vibrating in the XY plane, that's blue. That's measured in Tesla. So actually, electromagnetic waves have two different amplitudes measured in two different units. So don't worry about that one. We pick the amplitude based on what does it make sense to measure for the system. With light, it has electricity and magnetism together. It actually makes two of these transverse waves side by side. Okay, so when you get to it, how do we measure amplitude? You find the equilibrium position, you find the maximum height, and subtract them. So this is actually the two earthquake waves. One of the ways you could measure the amplitude of an earthquake wave is to look at a seismograph. A seismograph vibrates up and down when an earthquake comes by. In this case, we found the equilibrium position right in the center. And the seismograph, the device that's doing the measurement, well, it oscillates up and down and it went up to a maximum of 34 millimeters. So in this case, I would be doing the amplitude is equal to 34, that's its maximum, and the equilibrium was 0. So in this case, the amplitude of our earthquake wave would be 34 centimeters, or sorry, 34 millimeters. Yay, amplitude! Right. Now we'll talk about earthquake waves later, but there's different types of earthquake waves. There's P waves, which are primary and hit first, S waves, which are secondary and hit second, so P waves, then S waves, and then surface waves occur after and destroy all the property that's left behind. P waves kind of break up the ground. P waves put pressure on it and break up the foundation of your house. S waves will do this with the foundation of your house, so then shake it in the opposite direction, and then surface waves just shatter everything that's left. So when we talk about periodic motion, we know it's a motion that repeats itself, but an oscillation or vibration repeats itself around a specific point. We can describe that oscillation or vibration with amplitude. How big is that movement? But we could also express it in terms of its timeliness. Does that repeated motion take a long time, a short time? Is it fast? Is it slow? So here's how we can express it. There's two ways, and you'll notice that they're functionally the same measurements, but with just a little bit difference in calculation. Okay, way number one, we can measure the time period. How long does it take for one cycle? So what you would do to get time period is capital T. It's measured in seconds. You take the total time. Let's say you're watching the giraffe vibrate back and forth. You take the total time and divide it by the number of cycles. Right? Whereas, let's say you wanted to express how fast something is going. That's still an expression of time. We would call this frequency. Frequency is a new one. I know you've heard of period before, especially when we talked about like orbital motion, gravity, circles, but frequency is new. Frequency, its symbol is F, and it's measured in this unit called hertz. And it tells you how many cycles per second something does. If we were talking about like the beating of a hummingbird's wings at 53 cycles per second, or the oscillation of like the alternating current that comes out of your outlet at 60 cycles per second, we probably want to use frequency because that's a number that makes sense. We'd be like, all right, it oscillates at like when you play video games, what's a reasonable frame rate for video games?
I have no idea.
That's what I was thinking. 60 FPS, 60 frames per second. 60 hertz is a frequency. It gives you 60 different pictures per second. Yes. Old TVs, if you ever look at those, old TVs have frame rates of like 24 frames per second, which is enough to make out motion, but is like on quality. Right? So there's two different ways to express time. Let's give you an example of how to use each, and then we'll go and check out some demos. Okay. All right, so let's say I've got a pendulum, and this time I just took a GIF of this, I don't know, ball of yarn here. If I wanted to measure its time period, what I can do is grab my phone, pull out the timer, and this is actually how I did this. I pulled out the timer and I counted how long did it take to do 5 cycles. Now, fun fact, one cycle is one complete back and forth motion. So one cycle would start here, go to the other side, and come back. That's one cycle. So one complete cycle is there and back again. So what I did was I took my phone out and I timed. I'm like, okay, I need to measure how long does it take to do 5 cycles. This time it took 9.9 seconds to do 5 back and forth cycles. That means it took about 2 seconds per cycle. That's how to get time period. That's it. Yay. Yay. Actually, I think we measured time period maybe when we did like the flying pig demo. All right. We measured the time period by counting up how long did it take to do a certain number of cycles and then dividing. Alternately, let's say I wanted to turn this into a frequency. Frequency is the same two measurements, so it's still the 5 and the 9.9. But what I do instead is I divide number of cycles divided by seconds. So I took my 5 cycles divided by 9.9 seconds, and I get a fraction of a hertz. What this number means is it does half a cycle per second. So 0.505 hertz means it completes half of a cycle every second. So when you think hertz, right? Hertz as a unit has a really specific meaning. It tells you how many cycles get done in 1 second. Now, usually when we use hertz, we're talking about things that move really quickly, like a hummingbird's wings. This is super slowed down because hummingbird wings are at about 50 something times per second. So a hertz means that this completes 53 cycles, 53 complete wing beats per second. So make sure you get down definition for hertz. Notice that cycles itself doesn't really have a unit. And since cycles doesn't really have a unit, this fun thing happens. Sometimes you're going to see hertz, the symbol. You're going to see hertz, the symbol, sometimes written as 1 divided by seconds. Because cycles or beats or, rotations are not actual units with metric measurements. They're just things that occur. Right? So 53 occurrences per second. Sometimes you're going to see hertz written as 1 divided by seconds for that reason. So I would put a little note on that. You're actually going to need that for this lab later today. So like put a little star. Lab later today. Gonna need that number. All right, some hertz you should kind of recognize. Some hertz you should recognize. You should know it's about 60 hertz is the electricity from an outlet. It vibrates back and forth 60 times per second. You should probably know things like, sounds. When you listen to sounds, those are going to be on the range of like 10 to 15,000 hertz. If you're talking about sounds and it's anything above or below that big giant range, you and I can't hear it. Evolutionarily, we can hear sounds that humans are able to make. Right? It really wouldn't make sense if we needed to hear like super low whale noises because humans can't make that sound and they don't really pose a danger to us. We can communicate in those frequency ranges and we can hear in those frequency ranges, which I think is neat. When we start talking about light though, you're never ever going to see a light waves frequency. Those frequencies are on the order of like 10 to the 15th. So 10 with 15 zeros after it. Oh, that's a lot of zeros. Right. We're never going to see the frequency for light. We can model it. You can see like an example of a wave, but you're never going to see something vibrate that quickly. Our eyes just cannot do that. Right? So with that, I think it is about time to go check out some demos. Actually, I'll do one more and then we'll do a demo. A set of demos, many demos. All right, so period and frequency, let's say I knew one and wanted to get to the other. You know how in both cases I used the 5 cycles and the 9 seconds? In either case, if I had one and I knew the other, I could use this inverse equation. They're inversely proportional to each other. So what that means is that if something takes a long time, it has a slow frequency. If something has a really fast frequency, it takes a short time. So the inverse relationship here means something that takes a long time. Has a slow frequency, a small frequency. If something is very fast, then it occurs in a short time, small time period. So if you had one and you wanted to know the other, I can use this inverse equation, and I figured sometimes people get tricked on inverses, so let me just show you how to algebra this. Right. Let's say I had a sound. So this is a model of a sound wave. And do you see the little red dots? Kids here, it might be really tiny to see the red dots. Can you see the red dots?
Yeah.
All right, what I did for the red dots was I grabbed my timer and I followed one red dot. I counted how long it took to do, I think, 5 cycles again. And I figured out that each cycle took 4.538 seconds. It's very slow vibration. So I know the time period t is 4.538. But how do I solve for f, right? Some people get tricked on this because then they're like, oh, so the ones cancel and f is also equal to that. No, 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 no. We multiply by f on both sides. So this is 4.538 f equals 1. Then to get f by itself, I'm going to divide by 4.538 to get my frequency. If this were a sound wave, a pressure wave traveling back and forth throughout the room, this would be too low for me to hear. 0.22 hertz means that it does about a fifth of a vibration every second. This is too low for humans to hear. So if I have a time period and want a frequency, I can use this equation. If I have a frequency and know and want the time period, I could also use this equation. Okay, so with this, you're able to do problems 1 through 5 on homework 9.1. So let's go take a break. You try out these 3 new equations and various new vocab words in homework 9.1, problems 1 through 5.